So in this video, I'll be doing question 4 from the 1990 AP Calculus AB test. The question is, the radius r of a sphere is increasing at a constant rate of 0.04 centimeters per second. Note that the volume of the sphere with the radius r is going to be 4 over 3 pi r squared. Part A is, at the time when the radius of the sphere is 10 centimeters, what is the rate of its increase in volume? Part B is, at the time when the volume of the sphere is 36 pi cubic centimeters, what is the rate of increase of the area of a cross-section through the center of the sphere? And part C is, at the time when the volume of the radius of the sphere are increasing at the same numerical rate, what is the radius? So for part A, we need to find the rate at which the volume increases, and this is a rate of change problem. So, first thing I do is find a derivative of volume with respect to time. We know we need to do this because a derivative is basically finding the slope or the rate of change at a certain point in a function, and that's what we're trying to find here. We're trying to find the rate of change of volume at the point when the radius is 10 centimeters. So what we do is we do some basic power rule. We end up with dv over dt equals 4 pi r squared times dr over dt. And we know from the problem that the radius is 10 centimeters, and we know from earlier in the problem that the rate of change of the radius is 0.04 centimeters per second. So we just plug those numbers in, and we end up getting dv over dt equals 4 pi times 10 squared times 0.04, and that gives us an answer of 16. That gives us an answer of 16 centimeters cubed per second. So the volume is increasing at a rate of 16 centimeters cubed per second. Part B is going to ask us to find what the rate of change of the area through the middle of the circle is. Not the middle of the circle, excuse me, the middle of the sphere. So the first thing we have to do is we have to find the radius of the sphere at this time. So we just use our volume equation 4 over 3 pi r cubed. We plug in 36 pi as our volume, and we end up getting a radius of 3. Now again, we find the derivative with respect to time for area. So we get dA over dt equals 2 pi r dr dt. Plug numbers in. We get dA over dt equals 2 pi times 3 times 0.04. And that gives us an answer of 6 pi over 25 centimeters squared per second, or an answer of 0.24 centimeters squared per second, at which the area of the center of the sphere of the sphere is increasing. Now for part C, we have to find what is the radius at the point when the rate of change of volume and the rate of change of the radius are exactly the same. So we know this to be dv over dt equals dr over dt. And since we know what dv over dt equals, we can just plug that in because we found that in part A. So 4 pi r squared times dr over dt equals dr over dt. Now just solve the equation, and we know that dr over dt's cancel out because when you just divide one by the other, you end up getting r squared equals 1 over 4 pi. And that gives you an answer of the radius is going to be 1 over 2 times the square root of pi centimeters. That's your answer.